The cosmological constant problem presents this interesting flaw within theoretical foundations of modern physics. So Einstein originally included the cosmological constant to prevent the universe from collapsing. Since then, it's evolved quite a bit after Hubble discovered the cosmological redshift. The paradigm shifted into the lambda paradigm, the expanding Big Bang. And the cosmological constant kind of evolved into more of an energy. It's considered dark energy or the source of the expansion. It really indicates that a homogeneous universe cannot be stable. Even if you include some magical space energy to try to stabilize gravity, you can't do it. No amount of fine-tuning can fix it. What I mean by that is that there's like this, it's a subclass of problems within the cosmological constant problem. It's not just that the prediction for the value of the cosmological constant is off by 120 orders of magnitude. The cosmological constant itself is hypersensitive to any changes in the vacuum energy density and the renormalization procedure. So if there's any change at all, any adjustment at all, any minute adjustment to, say, the definition of the electron mass or quarks or a Higgs mechanism, any kind of fine-tuning with those shifts the total vacuum energy density by orders of magnitude. It changes it dramatically. However, your predicted observed cosmological constant wouldn't change. It shouldn't change if you change the definition of the electron mass, say. And so this is the depth of the cosmological constant problem. It invalidates the concept entirely. The only reason that it's still in modern physics today is that there's momentum and observations validate their opinions. But it's not a theoretically sound or coherent argument. Now, we can fix this, but we have to abandon homogeneity and the expanding paradigm. Sean Carroll and Neil deGrasse Tyson will just have to sit this out. We have to change the way we view gravity on a fundamental level. I suppose I should say that I have a secret superpower when it comes to general relativity. I don't know how to do an integral. I mean, I can do very basic integrations. But in my opinion, integrals are misleading when they're used in gravitational physics, especially cosmological scales. Integrals are only useful when you need to envision something like an enclosed mass. But an enclosed mass is not a real thing. It's just a useful classical approximation. That viewpoint is really only relevant for things like the solar system. But beyond that, the entire idea of an enclosed mass is nonsensical. If anything, balls of quantum fields are embedded inside quantum fields. It's not balls of mass floating in space. You're much better off if you just kind of view the whole system as one giant chunk of mass. But anyways, that's the way that I view it, and I think that it helps resolve a lot of issues. Because these boundaries are arbitrary. Gravitational boundaries are just human chosen coordinates. They're not real. But back to the cosmological constant problem. So it's the original stability problem that Einstein had in formulating his homogeneous static universe. They balanced the gravity from all the mass by giving the vacuum a certain amount of energy that would generate an anti-gravity. But this doesn't work. It's a failed solution based on false assumptions. There is no such thing as balls embedded in space-time. Mass is a continuous field. It is not a homogeneous ether. Mass density is a scale-dependent variable. In other words, mass density on the Planck scale is very high. And on the cosmological scale, it's very low. It's scale-dependent. So, how do you describe this as a universe? Well, first of all, you have to stop with this assuming that the universe is expanding or collapsing. The entire idea that the universe is expanding or collapsing violates the Copernican principle, in my view. Gravity both expands and collapses. It depends on the distribution of mass and energy. What's going on in one situation. When you model the universe as one big object, that's fine, but you're choosing a center when you do that. You can't have a preferred. You can choose the coordinate system if you would like, but you shouldn't include time evolution for that, because then you're choosing a preferred slice of time for a specific observer, which would violate this entire idea that we're not in the center of the universe. You want all points to be in the center and all points to be at the edge. You don't want any kind of preferred reference frame. And when you use a homogeneous mass density and then say that it collapses to a point, you're violating that preferred frame of reference. So what you want to do is use a scale-dependent mass density. And it's what this means. You create a profile, a density profile for a given point. So in other words, if you draw any line, now you can use null geodesics if you'd like, but all I like to think of it as draw any line and that'll represent your radial coordinates, or it'll be a reference line for your radial coordinates. And you want a mass density profile to represent for that radial coordinate. And you just assume that that radial coordinate goes to infinity. And then at any point along the R, you would define the average mass density for that R, for the volume having the radius R. And you would implement a realistic density profile. And when you do this, we can resolve the cosmological constant problem. But how do we find the exact profile? Like I say, if you just assume that the universe is static, then you have to have an explanation for the gravitational redshift. Or for the cosmological redshift. I gave it away. So you have to have an explanation for the cosmological redshift. If you interpret it as, instead of expanding universe, you interpret it as gravitational redshift, then now you have the density profile. And this is starting from first principles. This is using general relativity alone. It's basically the same as if we went back 110 years and started over, because we realized the cosmological constant didn't work. And so we're starting over with Einstein's static universe. Instead of homogeneity, we're using a scale-dependent mass density, and we align it with Hubble's law. And so I've done the work for you. This is the profile I've settled on. This matches a Hubble constant of around 72 kilometers per second per megaparsec. The profile is rho of R equals 3K divided by 2R, where this K is the coupling constant, is what I call it. And it's approximately 0.833 kilograms per meter squared, this density profile. This gives us a horizon at around 13.5 billion light years. If we formulate this as a solution to Einstein's field equations, it would look something like this. Basically, it's a Schwarzschild, modified version of the Schwarzschild metric. That's because the universe is very symmetrical, especially on cosmological scales. We get a Schwarzschild horizon that matches our horizon from the Hubble's law. It's not a black hole. It's a coordinate singularity. And this arises because of the observer's perspective in relation to the emitting star. So whatever your chosen coordinates are, this perspective will exist in some frame. For that extreme frame of reference, there's going to be an extreme geometry that comes along with it. For starlight, this will manifest as an extreme redshift right at the horizon. Z will approach infinity. And for the other perspective, so if you're not looking at starlight, if you're looking at just not starlight, then the horizon will manifest as a blue shift, and it'll be in the form of Hawking radiation from the horizon. Now, so in order to obtain the 2.725 degrees Kelvin that we measure in the cosmic microwave background radiation, I have to use the Z at 2 Planck lengths from the horizon in order to get that degree, because the emitted Hawking radiation is extremely cold for this horizon. And so you have to have an extreme blue shift, and that's from that perspective, if you're interested. I even have a calculator on my website. But at 2 Planck lengths from the horizon, this is what's important. We get that 2.725 degrees Kelvin. Now, even more compelling about this interpretation is that it connects to the holographic principle. So back in the 1970s, Bekenstein and Hawking discovered that black holes have entropy, and that this entropy is proportional to the area of their event horizon. It's called the holographic principle, and it kind of implies that all of the information within that volume of space, within the black hole, all of it can be described by the degrees of freedom residing on the boundary of that volume rather than within it. So this means the entropy scales with the area and not the volume. That's the important part. So the mass density for our profile scales according to, it's something like M of R is proportional to R squared. This means that it's not volumetrically calculated per se. It's more of a holographic encoding from the horizon. And so all points are within some reference frame where those points are the horizon. In other words, every point of the universe is both the center and the horizon, and everything in between. It's because in general relativity you can choose the coordinates, and so you have to have this invariant system. But regardless, what this means for us is that we can express our density profile like this, where rho of R is 3 times the surface density divided by R. So that's what that little symbol is. That's sigma, and that represents the surface density of the observable universe. A few days ago, I wrote a Substack article, believe it or not. So it was just a way for me to lay out the details of how I would go about normalizing general relativity. So it's not really a quantum theory of gravity. It's just an attempt at closing the book. My chosen UV and IR cutoffs come from the horizon and location of the Hawking radiation emission. So from all of this, we can get a scale-dependent vacuum energy density, sort of. And it mirrors our profile. We can then use that to solve the Einstein-Hilbert action, and we can get like I guess it's what that is it gives you a total number of quantum modes or whatever. But really it's what it is. It avoids the infinities. If you guys want to go subscribe there, I'll probably write more articles. Heck, I may even start charging for them one day. But now that I've kind of sort of finalized the model, I'll probably start making more content. I despise making content. I love doing research. I despise making videos. I don't know how to make them interesting. Editing is terrible. And there's a lot to do, so it's kind of overwhelming. You're welcome to email me if you want to help out in some way. That would be great. But let's review before I close the video up. So all I've done is, instead of homogeneity, we just acknowledge that mass density is scale dependent. And you can't just say that it's homogeneous everywhere. You have to say, well, it depends on how much where you're talking about. And that's essentially all I've done. From there, general relativity and first principles lead the way. The results are that we can obtain an exact match for Hubble's law with no adjustable parameters. We can recover the observed cosmic microwave background temperature, and we do so at 2 Planck lengths from our horizon. This is only possible within a narrow range of profiles and horizons. This immediately eliminates the Hubble tension. I've worked through all of the CMB anomalies. They can be resolved. Yeah, I think that this is definitely an explanation for all of the CMB anomalies. We eliminate the need for dark energy. For dark matter, this produces rising curves in spiral galaxy or within galaxy rotational curves. Now, that's not flat, but rising, is much better. It's in the right direction, but there's no dark matter in this profile. We would just need better explanations for galaxies to resolve the flat curve problem, but I don't even think it's a flat curve problem. Most galaxies show rising curves. And so this eliminates the need for dark matter. It provides a scale-dependent cosmological constant. And it's not really a cosmological constant. It's just derived from the distribution. It's just another way to describe it. But it does resolve the vacuum catastrophe. It mirrors the holographic principle. This also provides a UV and IR cutoffs, and we can reconcile quantum gravity or general relativity and quantum field theory. All you have to do is assume that mass density is a scale-dependent variable, which it is. You just have to follow the definition of mass density. Space-time has no ontological standing in this framework. Space-time is not a real physical substance. It's not a field. It's not an energy. It's not a physical thing at all. It's just a human-created tool used for describing the relationships of mass.